What is up, everybody? Gabriel here, and happy Easter. It's been, 3 months since I last posted something useful on the vlog, and I'm sorry. There are projects in the pipeline, and they're coming. It's just been a really busy couple of months, and unfortunately the vlog has had to take a back burner, but hopefully over this Easter break I'll get to put out some good videos for all y'all. A few weeks ago, I did something called Oxford Pathways Taster Days. And what this was is basically we had these high school kids come into Oxford and tour around and get a sense of what it would be like to be a student at the University of Oxford. And at these events, they invited some postgraduate students to give lectures of about 15 minutes on whatever they wanted, their subject matter, their research. And so I volunteered and I gave a little talk about, well, what I do, my research. And here it is. Hope you enjoy. Sure. Okay, second lesson you're going to learn from me is you need, in all circumstances, it's good to have a backup plan. I do not have a backup plan.
Did you leave your evaluation for now whilst during this last?
But okay, never mind. So, my name is Gabriel. At least the pen was work. My name is Gabriel, and I'm doing a PhD in something called particle physics. Does anyone take physics here? 1, 2, 3, 4. Okay, so we have half the class of physics. We're in year 10, right? Year 10. So what are we learning in year 10? Nothing. You can be learning nothing. Sometimes I feel like I'm learning nothing. Sorry? Yeah, what are you learning?
Oh, Newton.
Newton. Yeah, he's cool. He's a cool guy. What else?
Forces.
Forces. Yeah. Sorry. I try to do the accent, but they're really bad. So, yeah, Newton's fun, and then eventually you'll start doing stuff with like heat and electromagnetism, and eventually you get to something called quantum physics, which is really cool study of really small particles. So what happens at the quantum level, at the level of really small particles, is vastly different to what you're used to on the regular scales of matter. So let's say, I'm not as cool as I thought. Let's say we take this chair here, and we try to saw it in half, and then we try to saw it in half again, and all the way. What's the smallest bit of stuff that I can get from this? Yeah, but what, so we have matter, right? We have this, we have our chair, and then we try to cut it in half, and half. This is really bad. What's the smallest thing that I can get? Sawdust, okay. Let's take the sawdust and let's break that in half as well. What else? You get particles, right? That's exactly what I studied. I studied particles. And these particles, this sawdust, is actually made up of these little tiny particles all jumbled up together. And they're held together by various bonds, which you might learn in chemistry, but we're concerned with physics, which is both bigger and smaller than chemistry, interestingly. So you can take a look at these particles, and eventually we'll come to something called the atom. What does an atom look like? Does anyone know? Yeah, it's got a nucleus. So it's got electrons, right? So I have electron here, and these things. What exactly? So I have these in common. Let's see. So I have protons here, and neutron, and I have electrons. By the way, can anyone tell me what element is this? This is helium, right? Helium-4. So in an atom we have, this is called the nucleus, neutral, that spell. And this thing is the nucleus. By the way, fun fact, where does the word atom come from? Atom does not come from molecule. So who's aced their ancient Greek class? Anybody? Atomos is Greek for indivisible. And in the classical world, in ancient Rome, ancient Greece, they didn't know about this stuff. But they knew that probably eventually, if you sawed something in half all the way, you'd have something that's indivisible. And in the early 20th century, people figured out that there's probably an atom. And later experiments show that it looked like this. You have electrons orbiting around the nucleus, and in the nucleus you have protons and neutrons. And protons have a positive charge, electrons have a negative charge, and neutrons just hang about being neutral. So, on the whole, that's what atoms look like. Now, can I break this down even further?
Yes.
Yes, of course. If I ask this question, you know. Into what though? Subatomic particles, right. So what does sub mean? This is English. What does sub mean? Is below, right? So I can break this atom up into these individual components. You have the electron, proton, and the neutron. Can I break them up? Yeah, okay. Into what? What kind of particles?
I'm not sure, I'm not good at it.
Sorry? There are neutrinos, but not here. Good. So, I'll come to that in a minute. So, the electron itself, as far as we know, is a fundamental particle. That means if you take some sort of microscopic saw and you try to saw it in half, nothing will happen. The electron will just say, I'm fundamental, don't hit me. But the proton and the neutron, you can't. So, let's see, this is the red pen. Find the proton here by the neutron. They should be both circles. They are made up of particles, let me see. Right, so if you take some sort of big giant microscope, I don't know how you're going to build it, actually I do. But if you take some sort of big giant microscope and you hold it to a proton, you hold it to a neutron, you'll see that actually you can split them up into these things. So you have these U's here, you have these D's here, and you have these squiggly lines that let you go back in time. They don't. Back to the future reference, sorry. Okay. So these things are called quarks. This is called an up quark. And these ones, getting the hang of this. There's a story behind why they're called quarks. If you're interested, you can look them up on Wikipedia or in Bill Bryson's A Brief History of Everything. I can't remember what the story is. Now, these quarks, you have two up quarks in a proton and one down quark. And in the neutron, you have two down quarks and one up quark. And together, they somehow make the +1 electric charge and the 0 electric charge of the neutron. And in between all of these quarks, gluing the whole proton together, we have pinyl. They're called gluons because they glue things together. And you can be like, well, by golly, Gabriel, how do you know this? This is absolutely amazing. Well, remember when I said you have to take some sort of like giant microscope to these things to figure out what's inside? And that's exactly what we do. Our microscope is, well, have you all seen a microscope? Like these desktop things that you have in biology. So you put your cell on a piece of glass, you put it under the lens and you look into it like binoculars, and you see all those semi-dead things sort of wiggling around in the water, right? So those are the kind of microscopes that we use in biology. In chemistry or even in some levels of physics, we use different kinds of microscopes, like electron microscopes, which can be these basically room-sized machines that look at these really small things. My microscope is bigger. My microscope sits in the heart of Geneva. You know where Geneva is, right? Yeah. Geneva, Switzerland. It's shaped like a circle, and it is 27 kilometers in circumference. So I have this tunnel, which is basically the length of a tube line in London, 100 meters underground. What we do is we take protons, we accelerate them to really high speed, and you smash them together and see what happens. Yes. So this is called the Large Hadron Collider. We take protons and we smash them together and see what happens. And you can be like, but Gabriel, when you smash the protons together, don't you just get these things out? Like, what's so interesting about that? Well, let me tell you. If we draw a table of all the particles known to man so far, it would look something like this. So we have here the up quark, which we talked about earlier. We have the down quark, and we have the electron, which all make up all of our usual stuff. So this whiteboard, your face, my face, all made up of this stuff. Oh, and the gluons as well. We'll call it G. And in addition to this, we find that there are things called neutrinos, which you mentioned earlier. So this is the Greek letter nu, which is in English it's now the N, the letter N. And for some reason, some bizarre reason, there are, for every one of these particles, there are two more copies. So we have up, down, charm, strange, top and bottom. And then their copies of the electron are given funky Greek names. The electron, the muon, and the tau. And there are copies of the different neutrinos as well. So we have nu, sub e, sub that. And then this stuff that comes out of the light bulbs, that glares into your face when you're bored and you can't sleep. Light is made up of photons. It's the little particles of light, which also a Greek name, gamma. And there are other forces which mediate things like nuclear decay. So why do nuclear reactors work? Why does the sun even work? It's because of the particle that mediates something called the weak force, which no prizes for guessing is called the W particle. And then when they did some more experiments, they were like, there's more than, well, there's a positive and negative W particle, but also there's another particle which mediates a similar kind of force, but we don't know what to call it, so we just call it Z. So there's a Z particle. And then there's another particle called the Higgs, which was discovered in 2012. You can read up all about it. I see that some of you are taking notes. Thank you. I feel so appreciated that what I say is of value to you. You can also look this up on Wikipedia. This is called the Standard Model. And this is where particle physics stands today. With big microscopes like the Large Hadron Collider, we can take particles apart, and through funky quantum physics, what would happen is, for example, we take our proton, collide it with another proton, and what collides isn't the actual proton itself, but the stuff inside. So we could take, for example, a U quark would collide with another quark. U, and then they would collide to produce something. Oh, okay, let's write it like this. They would collide, and then produce some particle, for example, a Z, and then they could produce out, for example, something like this. And we're trying to make new matter, things that we don't see in everyday life. We know they exist. We take our protons, we collide them, and through some physicsy process, we make all this new stuff, and we study this. Questions we ask is like, how heavy are these things? How do these things interact? And how do they fit into the grand scheme of the universe? So, and this is a really important question. How does this all fit in? Because while we do have our standard model, and we have our stuffed particles, and we have particles that talk about how they interact with each other, there are still some big questions. How did the universe start?
No.
I saw a face, I saw a look in your face, you're like, oh, I know the answer to that question. Big Bang, right. So, the Big Bang is a theory that says, okay, about 14 billion years ago or so, long beyond the reach of archaeology, unfortunately, 14 billion years ago, everything that you know and love on this earth, and everything in the universe, in the vastness of the universe, was compressed into this little small space, and then suddenly expanded. So we have this little small thing that suddenly expanded to make our universe. But actually what happened here? What does it mean to have everything compressed into that small space? So it must have been kind of, I mean, there's no sense of personal space. I'm sure it would be very uncomfortable. What does that actually mean mathematically? How do we even describe that? What was the universe like? Or, another question. So I told you earlier that the proton looks like this. But actually I lied, it doesn't look like this. Because there are all sorts of random things that just happen. And using our big microscope, we can figure out these things. We can figure out what the stuff that makes us is. What is it really? And perhaps something even more interesting is that all the things that we know about, wood, rain, earth, the sun, this kind of normal matter is only about 5% of the universe. Isn't that amazing? That we say, we as scientists, we can talk quite authoritatively about what we do know, about the standard model. But what we do know is only about 5% of the universe. There's 20% of the universe that's called dark matter. It's this strange, unknown stuff. We can see it with our telescopes. Rather, we can see its effect in our telescopes. We know that it's there, but we have no idea what it is. And then you can ask, okay, 5 plus 20, that's 25%. What about the other 75%? The other 75% is something called dark energy. Now, it's not like some force or something that makes you shoot lightning out of your fingers. It's this thing that makes the universe expand and expand and expand with no end. And when you really think about it, this is kind of crazy, because when I blow up a balloon, right, it takes effort for me to put air into the balloon to make it get bigger, right? When we do our calculations, we see that, okay, our normal matter is kind of like this. Then where is the energy that makes the universe expand? Where does it come from? That stuff's called dark energy. And so, dark matter, dark energy, we have no idea what that is. Which is why we do experiments like this. Which is why we are interested in building these This is actually the largest machine in the world. And it takes 10,000 people to run to make it go smoothly. Yeah, I am probably one of those 10,000. And so, well, I just hope that you'd see that in physics right now, it's not something that's necessarily very far away, or very sort of hard to grasp. It's actually very connected with where we come from, who we are, why we're here. So if you like physics, or even if you don't like physics, give it a try. Come join me. Let's try to uncover the mysteries of the universe together.
All right, guys, who's got questions?
All right.
How does it take up 75% of like the universe if it's not happening?
Right. So we have this. What's the most famous equation in physics? Yeah. So this is actually at the center of a lot of what we do, E equals mc squared. And when I say that dark energy makes up 75% of the universe, what I actually mean is that it makes up 75% of the energy constant of the universe. Does that make sense to you? Yeah. Okay.
How would physicists go about investigating dark matter and dark energy, like find out what it is?
Right. So there are no programs currently to investigate dark energy because we have no clue what it is. Because it's like little, but we don't even know how to make it. We have no real sort of model of how it comes to be. But for dark matter, we can do something similar as to what I made earlier. We can postulate that maybe, okay, so I have some regular matter, and then say I have some funky thing like that then, how am I going to do this? That then makes something that I can detect, for example, and something that I can't detect. So I have regular matter going to some dark matter, and then this dark matter then decays into something I can detect and something I can't detect. So in our detector, have you learned about the conservation of momentum? No? Okay, so the things we can't detect in our detector, we can figure out that they're there, because when we look at something like this, we'll expect this thing to go that way and something else to go that way. But when we don't see that, we can say, okay, maybe there was something there, right? And then once we do this, we can look at our model, we can see, okay, what would the energy of this thing be? Where would it appear in our detector? Would it appear over there or over there? And then once we make, we can analyze the data and then finally count. We can say, okay, so I can count, I expect this number of backgrounds, and if the signal is there, then I expect this amount of signal. Then we look at our data and we say, and then it says, okay, oh, it's here. Well, this is not very conclusive. That's actually the status of a lot of our findings right now, is we estimate our background, we estimate our signal, and then we look in the data and we find that there's no excess, no great big bump. Does this answer your question?
Yeah.
You know how you say, like you said, that the universe expands, but what space does it expand into? Because that's the universe itself.
So that's a very good question, because even when we say balloon expand, it has to expand into the air around it, right? The fun thing about the expansion of the universe is that it is the universe